Okay, so human walking, multi-segment, pretty much completely well actuated body structure, but let's just focus on the point mass, the center of mass, okay? So for the human walking, the center of mass may be doing the trajectory like up and down, moving forward, okay? And how those mechanical works are involved for those motion. So the only external force for when we are focusing on the point mass is by the force, the contact with the environment, which is a ground reaction force here. So since it's a kind of repeated motion, we are going to focus on what's going to be the mechanical work per step. So from first initiation of the single support phase up to the next initiations of the next single support phase, we set it up as a 100% gate cycle. So that's what we are going to analyze the work per cycle. So you are starting from initial velocity v naught, and you are moving forward, your inverted pendulum moving forward. Before collision, you will have a velocity forward down with the amount of maybe mv minus. And after collision, you are going to change your velocity as mv plus forward and up. And your total mechanical work per cycle, per gate cycle, is going to be composed by the work provided during the single support and work provided during the double support. Okay, so as I said, there are a variety of actuation could be possible, but let's just focus on the hip torque actuation versus the ankle push-up actuation. So hip torque is applied during the single stance phase, okay? So single stance phase make those hip joint torques, hip muscle forces moving the center mass forward by the leg swing. And during double support, you are doing the ankle push-ups to the ground so that you can do the push-up impulse actuation. And those are the two actuation. And then there is a collision loss occurs. When you hit the ground for your new stance leg, the leading leg, there is a collision occurs at the heel. So we will make it as a H, as a heel strike impulse. This is the loss. These two hip torque and ankle push-ups are input, energy input provided, and H is the energy loss during the collision. Okay, so your single support work is going to be expressed by the W hip, and work during the double support is actually work provided and work lost. Okay, so W push up and minus W heel strike. Okay. Okay, how to calculate the work? When there's a mass and there's forces are applied, your work is, by definition, is the displacement integral of the force applied, or the angular displacement integral for the torques applied. More often, you can just measure the F and X and just integrate it, and then you can calculate the work. But often, it's challenging to calculate the forces. For example, if you want to collect the ground reaction force, you should actually measure all the ground reactions for your all steps, right? And then you can also follow the center the mass trajectories over time. So sometimes it's often easier, relatively easier to measure velocities than the forces and the displacement. So by the Newton's law, the work is equal to the change for the kinetic energy. We also obtain the work using the kinetic energy. So with that, so I have a velocity noted here, V naught. You know, have an initial kinetic energy, mv 1/2 mv naught square. And for collision, it's going to be 1/2 mv minus square, mv plus square after collision. So I can express those work in terms of kinetic energy change per step, per phase, gate phase, so which is going to be 1/2 mv minus before collision square minus initial velocity square. And during double support phase, before and after velocity, kinetic energy change will be equal to the push-off energy combined by the heel strike energy loss. Okay? Okay, so at this point, I'd like to split it out. How much portion of this total term, the kinetic energy change during collision, is contributed by the push-up, and how much portion of this is generated by the heel strike loss? To do so, we should do some assumption, because during the double support phase, the push-ups and heel strikes are, provided at the same time. Then you cannot really split it out, the contribution for each. So to make the problem simple, we are going to do the assumption saying that push-up impulse is immediately applied before collision. Okay, so it immediately precedes the collision, H. So P precedes the H immediately. Okay, that's our assumption. So we can split it out: immediately before, immediately after. So P is applied here at this stage, and after that H is applied. Okay, so for V minus, there is a P is applied, the impulse is applied, so your momentum changes will be from V minus to V star. Okay, so with that, after that, there is a heel strike collision occurs. So with the impulse applied, you will end up reaching to the V plus after collision velocity. Okay, so to split it out, the work contribution by the push-up and heel strike, we split it out using this assumption. Okay, so with that, let's examine if we could correlate the V plus in terms of pre-collision speed and or actuation input, the P, etc. Okay, for symmetric leg, this interleg joint angle is 2 alpha, and this, since those velocities are all square to the leg, I have those those velocity vector velocity vector angle as a 2 alpha as well. And from impulse momentum relationship, what I can get is the vector V minus plus P, the push-up impulse is going to be V star, and V star vector sum of the H impulse is going to be V plus. And also with the angle, okay, with this geometric configuration, we can get V plus in terms of V minus cosine 2 alpha and P sine 2 alpha. Okay, P to sine 2 alpha. Okay, so we could express after collision speed in terms of V minus and the push-up. And note that we don't need H components here to formulate the V plus in terms of V minus and the P. Okay, so for steady walking means like a repeated walking, what would happen is your V plus after collision velocity should match with the initial velocity, right? So this is a constraint that you have to walk on steady state. So V plus could be formulated as V minus and the P as well as the V naught. Okay. Okay, so for the original walk equation, we could formulate the walk in terms of kinetic energy change. So for each stance, single stance phase, push-up phase, and heel strike phase, we can formulate it in terms of kinetic energy corresponding to that. And there are so many velocity components here: V minus, V naught, V star, and V plus. We will just solve it everything in terms of V minus. Okay, so here we have a V naught in terms of V minus and P. Okay, we can plug that in. Here we want to calculate V star square minus V minus square. And if you look at this vector diagram of the V minus and the P and the V star, we can see by Pythagoras rule, V star minus V minus star minus square will be what? Simply 1/2 m P square, right? So we formulated all the work in terms of kinetic energy change, and also again in terms of V minus and the P push-up impulse. Okay, for steady state, what will happen is actually whole like energy throughout the cycle should be 0, right? Otherwise, your kinetic energy change will occur, means that you're either gaining the speed or losing the speed. It's not a steady state. So for the steady state, your total work sum should be balanced out, turns out to be 0. So what that means is your work input by the hip joint, torque, and the push-off should be matched with the collision loss. So this is the loss during the walk, and this is the energy input during the walk. So those two amounts should be balanced out for the steady state. Okay, Yeah, a little bit complicated. So if I just rewrite those work components, like a W hip is gonna be a function of P. I just rearranged them as a form of P, quadratic of the P's. Okay, so P square, V minus, and V minus square. And also your work by the ankle push-up is gonna be quadratic to the P square. And your total work input is going to be sum of those two. We can also formulate it this, and which is going to be also same as heel strike loss for the steady state walking. Okay, let's examine how those actuation variable P, how the magnitude of the P will affect the total work for the hip, push, and everything. So we are going to examine the total mechanical work per step in terms of the P as an x-axis. So your push, easier one, comes first as increasing quadratically, okay? So if you push harder, your push work increases a quadratic manner. Okay, how about the hip? Hip, if you have since you have a minus sign and a quadratic, so it looks like something like this. And those hip work reduces as you increase the push. So it looks like this. So it looks like a linear, but it's actually a very large quadratic form. Okay. So we can see hip decreases with the greater push and push increases greater push. So total work, the sum of those two, the orange color and the blue color is the total work input here. Okay. And then total work input actually reduces as you push harder. Okay. So if you push harder and harder, your mechanical work will reduce. So you can walk with small input, small energy input. Okay, that's fun. So it looks like even goes to 0 and go to the minus. What that mean physically? Well, your hip and the pushes are energy input to compensate the collision loss. So minus input doesn't really make sense. So we are going to only consider the case where all the works are in a positive range. Okay, so the range from here to the left-hand side. Since your total work seems to be monotonically decreased, this is the point where you can walk with minimal mechanical work, right? So minimal mechanical work, this what we call as optimal walking push-up. So optimal push-up with the amount of this will give you the least costly walking in terms of mechanical energy point of view. Okay, so what that means also is your push-up is generating all the necessary work and there is no hip joint work. Okay, so optimal strategy for powered walking is you apply the push-up actuation alone. You only use the ankle push-up, no hip. And what that means is since your energy input is to compensate the energy loss for the collision, your push-up, ankle push-up is perfectly compensate the energy loss during the heel strike. Since your energy balances are completely perfectly balanced during the double support phase, there's no extra work necessary during the single support phase. That's why you have a 0 W hip. Okay, now let's examine the amount of work required for the steady walking. So if you just plug those optimal P values here for the work equation and obtain the value, then you can see that those energy for the optimal walking is proportional to V square alpha square. Okay, compared to the case where you don't use the ankle push-up at all and only apply the hip torque for the walking, you will have like a 4 times greater mechanical work required to maintain steady walking. So even though it's a very, very rough approximation with the point mass approach, we can see that the energy supply by the hip is more expensive than the ankle push-up. Okay, so mechanical energy wise, push-up is more efficient than the hip actuation. Okay, well, that does make sense because when you apply the hip torque during the single support phase, what that means is you actually increase the speed. For energy, if there is no torques, your energies are conserved, so you're going to have a same V naught before collision. But by doing the actuation, you will enhance the velocity, and then that means you have a more downward vertical velocity that will give you a greater collision collision impulse from the ground, right? And then if you actually pushed up your velocity before collision, that means you have a reduced vertical components for the velocity, and it will reduce the collision loss. Okay, so heat powering increase the collision loss. Therefore, a push-up will be more efficient. That does make sense. Okay, so next step is this is totally mechanically analyzed interpretation for the human walking. Well, no human walking. It's a point mass walking, right? So you may wonder how this very, very simple approach could reflect the human behavior. Okay, so that's coming in the next slide.